Hi, welcome, 4th and 5th grade. We're going to talk about science. And today our focus is on gravity. Gravity is a force. And we're going to explore this a little bit more. So, I want to show you some things that I put together for us today. I took a kitchen magnet off my refrigerator. It's not very big, but it works. And I also found a paper clip and some string. And I attached the paper clip to my string and I put on happy faces. I taped some happy faces on both sides just so you could see it better at home. But if you don't have a paper clip at home, you can use key rings. I tried this out yesterday and they work pretty well with the magnet. I happen to have a laser key ring, keychain I should say, and it works. It definitely sticks to my magnet. I found a thinner one as well, and it also works with the magnet. And then I found this keychain. It also works really well with the magnet. So in one of the other lessons, maybe you watched from grades 2-3, I talked about pendulums, and you can use key rings or keychains with your magnets. For this lesson, and you could also use it to create pendulums or attach it to a string to have it go back and forth, swing it back and forth. Okay, so I'm going to use my paper clip with my happy faces here in my string, and I'm going to put my magnet near it. And maybe we can start to see when does the magnet start to pull on the paper clip here. How close do I have to get? Do you see it? So I'm pretty close. My magnet's pretty small, but it's starting to pull on it. I could even put my magnet on a ruler if I wanted to measure how close I would need to be for the magnet to start pulling on my paper clip. So I'm going to start getting closer and closer. When is it going to start to pull on it? Do you see right about there? That's about maybe 10 centimeters. So I want us to think about how a magnet is similar to gravity. Why don't people fall off the earth? Well, let's take a look here at a globe. So if the magnet is going to represent gravity, and this will represent us. So if I am somewhere in Canada, here I am in Canada. Gravity is pulling me here in Canada. If I start to travel from Canada down to where we are in New Mexico, gravity is still pulling on us. Let's say we took a trip all the way to the south. Let's say we went all the way to Chile. What is gravity doing? It's still pulling on us. Let me turn it this way. Maybe you could see it better if it's this way. So, as I travel across the globe, across the earth. Ooh, I lost gravity. Went out into space. There we go. And I'm traveling even to this southern part of the earth. Gravity is still pulling on me. And notice that gravity is pulling towards the earth. Actually, gravity pulls towards the center of the earth. What does gravity feel like where we are? I'm going to throw this ball down, and gravity pulls on it. What direction is gravity pulling the ball on? Down. If I was in Chile, in the southern part of the earth here, and I threw a ball, which direction would it fall? It would still fall straight down. So let's review our senses and go through some questions as we're starting to explore and learn more about gravity. So let's do a quick review of our senses. So our sense of touch. So I could feel the pull of the magnet. And maybe when you start playing with magnets that you find on your refrigerator or any other part like that, what do you feel? When do you start to feel the pull of the magnet? We're not going to use so much our sense of hearing or our sense of smell or our sense of taste at all, but we are definitely going to focus on our sense of sight. What are we seeing? So as you saw me putting this magnet close to my paper clip, I can get this to spin around. I can get this to follow. Wherever the magnet goes, our little happy face is going. How close am I getting to it? Does it affect the pull of the magnet? When I dropped this ball, when I took this magnet and I traced it across the globe here, what questions came to your mind? How about, what is gravity? We know it's a force. I'm going to talk more about that, but what does that mean? Is gravity the same here on Earth and on the moon, on Mars, in space? How about a what-if question? What if we were on another planet? Would we feel gravity the same way we feel it on this planet? Do you have a when question? When does distance affect the pull of gravity? When the magnet is close to my paperclip? When my magnet is away from the paperclip? How? How is it that anywhere I'm on Earth, gravity is always pointing downwards? Why? Why is it important to know about gravity? How does it help us make things in the world? Do you think it's important to know what gravity is, why it's important when we build things? Do we want things to fall down or to stay straight up? It depends on its purpose, right? So gravity is a force, and remember, force is a push or a pull. And a force, a push or a pull, can move an object, stop an object, or change the direction of the object. And so gravity is a force, and it causes objects with mass to be attracted to each other, just like the idea of the magnet and the paperclip. And matter is anything that takes up space and has mass, just like you and I. The Earth has a mass. The sun has a mass. All of the planets in our solar system have a mass. The building I'm in, wherever you are, everything has mass. And we can talk about mass, which is how much matter there is in something, which is different from weight. We have a mass and we also have a weight. So let's compare mass and weight. So our mass is how much of us there is. And how much of us there is isn't going to change if we're on Earth, if we're on the moon, if we're out in space, if we're on Mars. Our weight will change because weight is different from mass in that it's the force of gravity. And there's actually a mathematical equation that I want to share with you. So we can talk about weight is equal to our mass times, I'm running out of space here. I would keep writing this way, but I'm going to write it right here, multiplied by gravity. So our mass doesn't change, but does gravity change? Yes, gravity changes from Earth to the moon to Mars. So the planets and the stars in space are these huge, massive objects. And the sun is the most massive out of all of them. And it's so massive that it pulls in our planets into our solar system. And so gravity actually depends on mass, how much of something there is, and distance. And we could sort of start to see that with our magnet. So if I had a bigger magnet, a stronger magnet, more magnet, then that means that my paper clip would be attracted or pulled closer to the magnet sooner at a shorter distance, or I'm sorry, at a further distance, we would start to see the pull. But I have a smaller magnet, so I have to get pretty close to it. And so our massive sun, which is far away from us and far away from other planets, is so massive, though, that it can pull other massive objects close to it. And so you can see the difference here. These are gravities, a gravity on Earth, the gravity on the moon, and gravity on Mars. And so here's a question for you. If our weight is our mass times gravity, and our mass, how much of us there is, doesn't change, whether we're on the Earth, the moon, or Mars, but gravity does change, then where would we weigh the most? On the Earth, on the moon, or on Mars? Where would we weigh the least? On Earth, the moon, or Mars? So I want to show you something else that maybe you haven't seen before with the units here for gravity. So Earth has a gravity of 9.81. This is the way we would read this, meters per second squared. The moon has a gravity of 1.62 meters per second squared. So these might be new units for you. Maybe you're familiar with the meter. We need to be right now 2 meters apart, about 6 feet. So 1 meter, about 3 feet. And then Mars is 3.71 meters per second squared. Okay, so lots of ideas here. So let's think about all of these things as evidence. And evidence is information that supports our idea. So the big idea here is that gravity pulls us and keeps us on the Earth. It's a force. And we have a weight made up of our mass, how much we have, how much of us there is, times gravity. Gravity changes depending on where we are in our solar system, in space. Gravity always pulls objects down. Why don't we float off the Earth? Because of gravity. Our Earth is round because of gravity. And as we travel, gravity always pulls objects towards the center of the Earth. So here's another diagram to show what I've been talking about and what we've been exploring. So here's an example of the Earth, and we can see that gravity is being represented by this arrow here, this force. And we are always going to be pulled, objects will be pulled towards the center of the Earth. What does that look like, though, when we're on the surface of the Earth? It looks like things are falling downwards. So I challenge you to look around you, to think about, and maybe do some research, if possible, using some technology, computer, a phone, a tablet, to look at gravity on other planets, on different moons, and ask yourself, would you weigh more or less there? What would that feel like? Think about the astronauts as they go higher and higher away from the Earth. What's happening to them? What do you see? Do you see them walking in space the way we walk on Earth, or do they seem to float? Why would that be? What about astronauts on the moon? Have you seen anything on that before? Do they look like they're walking the way we walk on Earth? Was there something special about what they were wearing that kept them on the moon? Did they seem to bounce on the moon? So I challenge you to draw your own diagram explaining and showing your learning for today. What is gravity? Why don't we fall off the Earth? Why is gravity always in a downward direction? How is gravity a force? What's the difference between our weight and our mass? So thank you for joining me today, and until next time, I hope you have a great day.
Hello, and welcome to At Home with APS. I am Mrs. Sears.
And I'm Mrs. Gaudette.
And we are here for mathematics today. So you may have joined us in a previous episode when we have done this particular routine. The routine that we're going to get ready to get set up to do is called Which One Doesn't Belong and Why? So if you've had joined us before, you had seen that there are 4 different numbers on our board. Sometimes it might even be a picture, but in this case, we are doing numbers. What's one thing that you notice about these types of numbers that we have? They're fractions. Wow, I don't think we've done one with fractions before. So we're going to talk a lot about different characteristics of the fractions as we go through and kind of explain which ones don't belong and why. And if you remember, the kind of the plan that goes along with this is that they could all not belong, right? And there may be ones that have more reasons why they don't belong than others. But I'm going to start off by saying...
You know something? Am I on?
I think so.
I know one thing. You gave away.
I did?
We didn't want them to know that none of them don't belong.
They all could not belong in some little way, shape, or form. But I think I'm just thinking about, first of all, let's talk about the different numbers that we have. So we have a 1/2. I'm going to stand right here. We have 5/3. We have 2/10 and 2/5. So if I was to start off with one right away, I mean, the one that I think that kind of looks like it doesn't belong right away to me is the 5/3. And the reason why I think the 5/3 doesn't belong is because it looks kind of top heavy. It's what we would call an improper fraction, right?
Maybe.
So when you have an improper fraction, isn't it that the top number is bigger than the numerator is bigger than the denominator, and it's greater than 1, right? So I could do something with this 5/3 and say that I don't think it belongs in the other ones because the other ones are all lesser than 1. It's the biggest one.
Okay, well, I disagree. I think that one fits.
Yeah?
I think a 1/2 doesn't fit.
I was going to say that one too.
And I don't think it fits because it's a unit fraction. Do you guys remember what a unit fraction is? Right? It has 1 in the numerator. So that is the only fraction that does have 1 and the rest do not.
So it doesn't belong.
It does not belong.
Huh. Well, since I went for the biggest one, I think I'm going to go for the smallest one. Because this one is the smallest. 2/10 is smaller than all the rest. I can tell because the denominator has the largest amount of parts in it. So it being a very low number in the numerator means that it's going to be at the smallest of the fractions.
Okay. All right.
2/10 doesn't belong because it's the smallest.
You know what? And I think 2/5 doesn't belong. And my reasoning is there's 2, and I'm going to have to switch spots with you really fast, Miss Sears. So I see a 2, and other fractions also have 2, either in the numerator or denominator. And there's other fractions that also have a 5. So my 2 and 5 are repeated in other, and all the other fractions have a number that is not repeated. So I think 2/5 doesn't belong.
Well, let me play with that 2/5 because this is what I like to do. I like to play with the numbers. So if I multiply the numerators and the denominators, so the top 1/2 would be 1 times 2 or 12. Well, 1 times 2 would be 2. Let's say 5 and 3, 15. 2 and 5, 10. 2 and 10 would be 20.
Wait. Can you explain to me what you were just doing? You just started to rattle off these random numbers. I'm not understanding your thinking.
I'm thinking I'm multiplying the numerators and the denominators, but now actually if I kind of played with it, maybe I want to make the numbers together. Well, so if the 1 times the 2 would be a 2, 5 times the 3 would be 15, 2 times 5 would be 10, 2 times 10 would be 20. This would be the only one with a single digit. But I was kind of thinking something else. I started off thinking something else when I was doing it.
Let's not give it away to them. Let's let them think of some reasons why this does not belong.
I think that's a good thing. If you can think of some other reasons why this doesn't belong, why don't you give us a tweet at home with APS, or you can actually send in some more ideas at your aps.distancelearning@gmail.com. And I'll let you take the rest away.
All right, last time I was with you guys, we had read part of a story and started some work on that. So I have the book that we started to read last time, which is Anno's Magic Seeds by Mitsuma Anno and illustrated by that person. And it is published with Penguin Putnam Books for young readers. So what this book had started with was Jack was a young man walking down the road, and a wizard came up to him and gave him 2 seeds. And the wizard told him to cook one of the seeds and eat it, and it would feed him for the whole year. He would not be hungry. Then take the other seed, plant it in the ground, tend to it for a year, and it would bloom to 2 beautiful flowers, 2 beautiful fruits, then comes 2 more seeds. So each time we'd plant it, every year went by, he'd eat 1 seed, plant 1 seed, and 2 seeds would be produced. And then Jack started to think about it. Jack started to say, this isn't going to quite work out for me because I'm always doing the same thing. And I'm getting the same results. So he thought, this year, I'm going to take both seeds and plant it. And then I will figure out what to eat for that year. Well, we had started that where we had that he planted both seeds and he ended up getting 4, right? So 2 plants, each plant produced 2 seeds. So we doubled our amount. And then it went to the second year. He ate 1 and planted the rest. So that was 3 seeds. And he got 6 seeds. And then it just kept going. And after year 5, we had discussed, wait a minute here. If this pattern was supposed to continue, how many seeds would he have after 10 years? I had left this work with you to try to figure it out on your own. So hopefully you've worked on it and we can work it out together to see if you are correct in your thinking. If you have not had a chance to do that, go ahead and take a minute. You can see our pattern happening here, which was that repeated pattern. Whatever he planted, he got the double amount of seeds. So pause me and go ahead and try to work it out to 10 years. And then you can see if you were correct. All right, I'm going to jump right into the work, and I'm going to go ahead and work on this one. So after year 2, he planted 5 seeds. If I plant 5 seeds, knowing that each plant will produce 2 seeds, 2, 4, 6, 8, 10. So we have that 10. Then Jack, of course, is going to say, hey, I need something to eat. I'm kind of starting to get hungry after a year. So he eats 1 seed. So how many will we plant? 9. All right. Then we continue with that pattern. If we have 9 planted seeds, how many seeds will be produced? Double it. Very good. Thank you. So we have 18. Jack eats 1. 17. So then we continue this to our 10 years. The numbers, so I'm going to just start at year 5. We have that. We double 17. Uh-oh, yeah, you notice now it's starting to get a little harder with our math here. Double 17, we get 34. So how many will Jack eat? 33. Thank you. So double 33. Thank you so much. 66 for year 6. Jack eats 1, so we have 65. I can still double 65 in my head, so we're going to continue with this one. So year 7, he had 65 that he planted. Each plant produced 2 seeds. So 65 doubled is 130. And then from there, we have 129. Thank you for mentioning that to me, that Jack will eat 1 seed. Now here comes in the tricky part. Now we're going to have to do some quick mental math here. 120 doubled. You notice I'm taking out the 9. Why would I take out the 9? Right, 120 is easier to double, and then I can work with the 9 afterwards. So 120 doubled is 240, and then 9 doubled is 18. 240 and 18 make, thank you, 258. Oh, thank you for pointing out that I keep forgetting the years. So Jack eats 1, 257. So do you think our 10th year we're going to have, remember you guys said you thought it'd be 50, 100 last time. Someone said it'd be 1,000,000. Did we hit the 100 mark already? Yeah. Did we hit the 1,000,000 mark? No. Do you think we're going to hit it? Maybe, maybe not. So now you probably have more of a reasonable estimate that you think it might be. So let's go ahead, year 9. Let's double 257. So I'm going to double 200 because that makes it easier on me. 200 and 200 make 400. Then I double 57. Well, I'm going to double 50. 50 and 50 is 100. So I have 400, I have 100, and then I have double 7, which is 14. So 4, 500, 514. Thank you for doing this quick mental math with me. So Jack eats 1. All right, I hear someone saying, it's about 1,000, it's about 1,000. I can already see that. How do you know that? Right, double 500 is about 1,000. So we know it's 500 and 500 is 1,000, and then 13 doubled is 126. And then, of course, if we continued our table, Jack would eat 1, which is 1,025. So how many seeds did Jack have after 10 years? Thank you. 1,026. So let's see what Mr. Anno did with the book, because remember, we didn't finish it. So let's see what happens with Jack in this book. So then in the spring of the 2nd year, after his discovery, 3 sprouts came up, and in the fall, 6 seeds were made. That winter, Jack ate 1 seed and buried the other 5. He made a noisemaker to scare away the crows and the sparrows so that they wouldn't come and eat the seeds. When the wind blew on it, the noise startled the birds. Now, last time, I kind of left out what Mr. Anno had. He has some actual questions for us. How many fruits will grow in Jack's garden next fall? We already know that answer, right? It's kind of up there. Well, the next year, that is, the 3rd year after he got the idea, all the sprouts came up in the spring. And in the fall, 10 seeds were made from the 10 marvelous fruits. In the winter, Jack buried 9 seeds in the ground. He baked 1 seed and ate it. The next year, the 4th year, In the spring, there came the sprouts, and in the fall, there were 18 seeds. That winter, Jack buried 17 seeds in the ground. The next year, that is the 5th year in the spring, all the sprouts came up, and in the fall, the new seeds were made. That winter, Jack ate 1 seed, and he buried the rest of them in the ground. How many seeds did he bury? Thank you. The next year, the 6th year, all the sprouts came up, just as before, and that fall many seeds grew. So many that Jack didn't bother to count them anymore. While he was busy gathering in his harvest of seeds, a nice young woman came along. Her name was Alice. Alice stopped to help him. How many seeds grew that year? Jack ate 1 baked seed, and so did Alice. And that winter, they buried the rest of the seeds in the ground. How many seeds did they bury? In the spring of the next year, the 7th year, all the sprouts came up. And in the fall, there were many seeds from all the fruits. That winter, Jack and Alice got married and held a wedding party. They gave 2 delicious magic seeds to each of their 5 guests. Each guest saved 1 seed for a souvenir for this happy day. Jack and Alice ate 1 seed each. That year, they also built a little storehouse and put 16 seeds in it to keep for a while. The rest of the seeds they buried in the ground. How many seeds did they bury? The next spring, the 8th, a lot of sprouts came up, and in the fall, many seeds appeared. And then, because they had quite enough seeds, they decided to sell some at the town market. They took 60 seeds to sell, including all of those that they had put in the storehouse that year, the year before. Then they put 34 new seeds in the storehouse, set aside 1 seed each to eat, and buried all the rest of the seeds in the ground. How many seeds did they bury in the ground? The next year was the 9th since Jack had his great idea. In the spring, a lot of sprouts came up, and in the fall, a lot of seeds were made. That year, their baby was born. So in the winter, 3 seeds were eaten, since each of them ate 1 seed. Now, because they had so many seeds, they went to the market to sell 100 of them, including all those that they had kept in their storehouse. They put 51 of the new crop of seeds into the storehouse and buried all the rest of the seeds in their field. How many? The next year was the 10th. The baby was growing, so Jack and Alice built a new, bigger house. In the fall, their field was filled with plants bearing the magic seeds. Soon it would be time for the gathering of their harvest. But suddenly, "Oh," said Jack, "the wind is blowing awfully hard." It was a hurricane. They had never expected such a terrible storm. The river overran its banks, and soon there was a flood. Jack tied the house firmly to a tree so it would not be carried away. Then he pulled the cow up onto their cart, which was now floating like a ship. Alice, holding their little boy in their arms, ran up to the attic of the house. Jack managed to scoop up a small bag of seeds. He tied the bag to the tree. What a dreadful storm it was. The wind shook the trees and blew the rain against them. Soon the field looked just like a wild sea. The wind roared and the dark, muddy water rumbled and rolled over the plants, the crops, and the storehouse. were completely washed away. Finally, the storm was over. The sky cleared and the sun came out. But the fields were empty and bare. "Still, our baby is safe. I am glad for that," said Alice. "So am I, very glad indeed," said Jack. "And our cow has survived, and I was able to save 10 seeds. So cheer up, dear wife. We will start all over and make a new life together." Jack baked 3 seeds. He gave 1 seed to Alice and 1 to their child, and he ate 1 seed himself. He buried the rest of the seeds in the ground. Jack and his wife then bowed their heads and prayed together for a good crop. And that is our story of Anna's magic seeds. We will be working on now a new game that we would like to introduce to you guys.
Okay, hello everybody. My name is Miss Obenchain, and today I'm going to teach you a game called Quick Draw, or sometimes it's called Speed. This is a game for practicing counting in multiples, and so we're going to practice today with counting by threes. Let's see, maybe we can put that up here. So the multiples that we're going to be using are 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. You can download cards that you can make from our website, or you could make your own by just taking a piece of paper and folding it in half, and folding it in half again, then fold that in half and in half again. And when you open it back up, you have 16 slots. So you could make 16 cards from each sheet of paper. So you'll need about 2.5 sheets of paper. And then when you do that, you're going to put the multiples on each of these. And you need 4 of each multiple. So 3, 3, 3, 3, right? These cards are set up with, they have 3 3s, they have 3 6s, then there's 3 9s, 3 12s, or not 3, 4.
Okay.
4 3s, 4 6s, 4 9s, 4 12s, 4 15s, and so on. So that's what you'll need in your deck of cards. And like I said, you can either make them and then just cut apart these different little cards, or you can print them out on our website. So I am going to shuffle these cards up really well because I've got those 3s and 6s separated. So I'm going to sort of move them around a little bit, make sure that they're mixed in, and then I'll shuffle. I'm not a card dealer here.
Remember if you were here that first week, card shark, card shark.
Okay, and so then how you set the game up is that when you do 4 of each of your multiples, and there are 10 in my set of multiples here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers I'm working with. 4 of each of those, so you're going to end up with 40 cards. And you're going to take and divide your cards, 15 to each of the players. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So now we should each have 15. And then with these leftover cards, you're going to divide those in half. So you should have 2 stacks of 5. Okay? And normally you would just play on a table like that. I'm going to bring these up here, and we're going to play up here so that you can see what's going on. Out of your deck or your partner's deck, they can have 3 cards showing at a time. And so we'll put ours here so that you can see them. So these are going to be the 3 cards I get to start with. And these are the 3 cards that Miss Gaudette gets to start with. And we can always have 3 cards showing. So when we use some of these cards, we can put new cards back in there. But you can only have 3 out at a time that you can work with. And then these are our start piles. And so Miss Gaudette will flip one on her side. And we have a 6 and a 30. So we can play the multiples before or after each of these. So on this 6, I could play a 3 or I could play a 9. On 30, we don't have a multiple after it, so I can only play a 27. So you can go forward or backward with your multiples. So now it's just speed. So we just take our time when we play through whatever we can play, and then we can add new cards here out of our deck. And I'm stuck, so I just can't play anything until something shows up here. Miss Gaudette is stuck, and then that's what we use these cards for. So we flip from that again and see. And we can play on either of these. I can play that. I can play this. I can get new cards out. And we're both stuck again, so then we're going to flip from here to get the game going again. And we'll have to flip again. Maybe I didn't do a good job shuffling. I can play 18 on that. Stuck again? Mm-hmm. Okay. Oh, I could play 18 there. And, oh, I can play 27 there. Do you see any cards that we can play? I think we might be stuck again.
Oh my.
And my cards ran out, so I'm going to just flip these over and use this again. And we'll do the same thing with yours. And she got me while I was...
Oh.
And I can put some new cards out. I can put 9 there. I can go back to 12. I can go back to 9.
No! There we go.
Oh, she got me there. There's the speed element of this game for you. Let's see, that's a 21, so we'll turn it up right. So we're both got 2 cards up here that we need to play, so we're going to just flip until we see something that we can play. Oh, I can play this one. Yeah. Okay. And I'm out of cards, so I won that game. So that is how that game goes. The directions for that are on our website for you, and then a template for making cards, or like I said earlier, you can just make these cards on your own. And we'll be right back.
Hello students, my name is Miss Becky, and today I'm going to be sharing with you a math activity called Starburst number. What you need to do this activity at home is just a piece of paper, regular paper, scratch paper, whatever, and a pencil. That's all. This is a great activity because you can do it with all different kinds of numbers and all different kinds of mathematical skills. It's a very flexible activity. Today we're going to do this activity with 3/4. So what I want you to do, and you can do it along with me at home, I'm going to model on this piece of paper, but get your piece of paper and work with me. First, you're going to fold your piece of paper to divide it into quadrants. I don't call them squares. It's not a 4 square because they're not squares, but they are quadrants. So you're going to first fold your paper into 4 equal quadrants. Mine is just divided with a marker. Yours can be folded. And then you can trace over those lines with your pencil. And then on the inside, we're going to draw a little star. I do know that drawing a star is hard. Mine's not perfect. I bet yours isn't perfect either, but that's okay. If it's even close to a star, call it good enough. In the middle of the star, we're going to write 3/4, because that's going to be our focus number for right now. That's the star of the show. So go ahead and make your quadrants nice and neat. But I actually want more than 4 sections because I'm going to explore that number in more than 4 ways. So I want to explore that number in 8 ways. So we're going to take each of these quadrants and we're going to actually divided into 2 more parts. So now, rather than having a paper that is segmented into 4 parts, we've got a piece of paper that's segmented into 8 equal parts. So we're just going to take this number, 3/4, this great fraction, because I know earlier in the lesson you were studying fractions, and we're just going to express it in lots of different ways and make sure we really understand this fraction inside and out. So the first thing we're going to do is we're going to take this number and we're going to use this first section up here and we're going to label it. So I want you to go ahead and write label it. And then we're going to take our fraction, 3/4, and we're going to write in what we already know about it. The 4 is our denominator, right? Oops, I ran out of space. Denominator. And our denominator, in our mind, we know the denominator tells us how many parts the whole has been segmented into. And then the top part, we want to know what we're talking about. That's the numerator, right? And the numerator tells us how many parts we're describing or how many parts are important in this moment. So that's our first job, is to label it. Our second thing we're going to do is we're going to draw it out. And in my own teacher mind, I'm thinking that would be called the area model. If we have like, the old, like a pizza, and we're dividing it into 4 equal parts, and we're describing 3 of them. That's an image that describes 3/4. The star of the show, right? After we draw it out, then I'd also like for us to put it on a number line. Let's do that next. So this next chunk is going to be number line. And 3/4 is more than 0 and less than 1. So that's our number line is going to go from 0 to 1. So there's our 0 and there's our 1. We're going to have that number line chunked into 4 equal portions. There they are, 1, 2, 3, and 4. And we're describing 3/4. So we're going to find 1, 2, 3 parts right there. Let's make sure that 1 is clear. Mine's not so clear. That's the way it looks when we describe 3/4 on a number line. The next thing I'd like you to think about is 3/4 as a portion of a set. So a set would be like, an example would be, say you have building bricks, little plastic bricks, and 3/4 of them are blue. That's an example of a portion of a set. Also, you could think like if you have little candies or something, and you keep 3/4 of them and you give 1/4 to your little sister. That's portions of a set. So what it means is maybe you have 4 items, and 3 of them are being described. The numerator tells us how many we're talking about. But of course, a set might not always be just 4. Maybe it's actually 8 items that you have, and that's okay too, if you can still see that set as 1, 2, 3, 4 equal parts, and 3 of them are being described. So that would be portions of a set. We'll call it set here. Another way I'd like you to explore this fraction is also adding. So we're going to, let's call it adding up to. So we're going to add up to get 3/4. So I might think, well, 1/4 plus another 1/4 plus another 1/4. If I add those all up, I'm going to have 3/4. And I can see this adding example, I can see it up here. I can use this to understand it. 1/4 plus another 1/4 plus another 1/4 adds up to 3/4. The next way I'd like for us to check it out is subtracting down 2. DOWN, down 2. I'm going to have to work on my penmanship. That's tricky for me. So again, you don't have to understand a complicated algorithm to see this or have been taught necessarily. You can look up at your example and you can see if I have one whole pizza and I take away 1/4, I'm left with 3/4. Let's just write that. 1 whole minus 1/4 will leave us with 3/4. Yeah? Makes sense? So another way that we can explore this fraction is by explaining it in words. So in words is always the trickiest part, I think. Not for everybody, but for some of us. So you think it through in your mind, maybe say it out loud to yourself like, 3/4, maybe you just tell what you know about it. It's more than 1/2, but it's less than 1 whole. So you just write down a few things that you know. Sound good? And then the last way, I always like to leave space for students to get creative. So think of a way that you could express 3/4. You know, there's this one, right? You could say, draw 4 little faces. 3 of them are smiling. 3/4 of these kids are happy. You could get it creative and express it however you want. I'd like to tell you that you can also use this activity. I call it Starburst number. You can use it to express all different kinds of numbers, different fractions, or even different whole numbers, and just come up with ways to express it. You can also do this activity with a partner. You could just come up with your own Starburst number, and then you could cover it and leave that as a mystery. And then your partner could go through and think through if they think all your different expressions are accurate, and then they could check your work and say, oh, yep, that's definitely 3/4. So I like this activity because it's fun. It is creative, and you can use it in a lot of different ways. So that's Starburst number. I hope you guys will take a chance to practice it on your own, use it in different ways, try it out with a partner, try it out with a friend. I think this could be really fun for you. So again, we practiced today using an activity called Starburst number to practice using one value. In this case, it's a fraction. Experience it and learn it in lots of different ways so that you really understand it from many perspectives. This would be called like a circumspect view. You're looking at this number from all different angles, getting a circumspect view of the number 3/4. But you can use it in many ways. You could use it with a different fraction, like one of these. You could use it with a whole number, like 100. Come up with 8 different ways to make 100. You could use it with a mixed number. If you understand mixed numbers, you can use it in all different ways. So I hope you guys will experiment with this activity at home and use it as a great practice opportunity. Next time we come together, maybe we'll have a chance to do it together using a different number. Meanwhile, I hope you'll practice it at home. Do it with your siblings. Try it with something easy if you have a younger sibling. Try it with something hard if you have an older sibling. See if you can catch your parents in an error. Good luck, students. And I'm really glad that you could join us at APS at Home. I hope you'll come back again. I hope you're staying safe and being very careful at home in your homes. Thank you.